In the previous segment, we did some mathematical manipulation to convert the parametric equation of the transformed stresses so that we could see emergence of a circle. That means the sigma and the tau. If you take the sigma, that the normal stress to be the x axis or the abscissa, and the ordinate or the y axis to be the shear stress at different orientation, then they lie on a given circle. So, that is what we saw in the previous segment. Now, obviously you can use, and then we also derived certain equations like this. So, to figure out these values, the principal planes, principal stresses on those planes, maximum shear stress, all those things we derived mathematical expressions for. But then there is a technique which is completely geometric in nature. That means given the known state of stress, you can start drawing geometrically, obviously in proper maintaining proper scales and everything, and then you can read all these unknowns from that drawing itself, and that technique is called the Mohr circle. And obviously we are now discussing for the special case of plane stress. Okay. So, that we will be discussing in this segment. Okay. Let us see what do we mean by the plane stress. So, that means we have our elemental square, or in fact a cube in this, okay, which because the other stresses are not there, it looks like a square, and then on that we have defined our sigma x, then sigma y, then we have tau xy and tau yx. Okay. So, this is the point P, about the point P. So, always you should think that you have to shrink this to that point, so that the stress is defined at a point, though we always draw a square or a cube in 3D. Okay. Now, the method of drawing the Mohr circle goes like this. You take some scale depending on the values of sigma x. So, that means you start with the knowledge of the state of stress at a point. For example, that means you have conducted some experiment or did something and you know these values maybe. Okay. Suppose all these values are known, and then what you do and how you find out the other unknown things. So, by choosing a particular scale, you draw an axis, okay, on which the right hand, the x axis will represent our sigmas and the y axis will represent our tau. Okay. Then by considering the directions which are shown in this picture are considered to be positive, okay, conventionally. So, because I am drawing a convention, so let me also draw these things: sigma x, sigma y, and this is tau yx and tau xy. So, these are the positive sense of both the normal and the shear stresses on every plane. If this is the case, then for that what you have to draw is, how to start drawing is, you take a point x whose x coordinate is sigma x and y coordinate is negative tau xy. Okay. That means this point will for such positive values, if this is considered positive, this point will lie below the x axis. That means somewhere something like here maybe. Suppose this is the point x given by sigma x and minus tau xy. Fine. Then you plot the point y maybe given by sigma y and tau xy. Yeah, let's assume for without loss of any generality I can assume this, maybe sigma y is less than sigma x. So, this height will be less than this, maybe somewhere here, and still I am considering that sigma y to be tensile. See, these are tensile stresses. So, all these sides are positive, tensile is considered positive. So, this is it's wrong. Sorry, because this height is the tau xy. So, I sorry for that. Yeah, the height has to be same, you know. So, the sigmas are measured on this. So, this or white color. So, this distance is sigma x and this distance is tau xy, okay, magnitude wise. Similarly, the tau xy, because the values are same, it will remain the same for the point y magnitude wise. It will just be above the x axis, the same height somewhere here, and the y is the sigma y is this basically, okay. I will draw it here. So, this is your sigma y and this height is again tau xy. So, this point is your y. So, this point is y. As soon as you draw that, what you can do is you can draw a line joining them and then you get the center of your Mohr circle. Because see this is sigma x, this is sigma y. So, the average of that, this point is given by sigma x plus sigma y over 2. And if you remember, our circle had a center at sigma x plus sigma y over 2. So, this is what I was talking about. So, sigma x plus sigma y over 2 is the center, and that is what you have got that location. And now, if you again, okay, I should have shown it there itself. You see here. Now, this point is like the point x and the diametrically opposite point is like the point y, right, because they are 90-degree apart on the actual physical condition. So, they are 180-degree apart on the circle. So, if we see here, so these are those 2 points which must lie on the circle. That means we have also got the radius of the circle. This is the radius. So, with that being the radius and that the center, now what you can do is you can draw the circle. Now, if you draw that circle, that is your Mohr circle, and then everything, all data now you can read directly from this picture. Like what? See, if I go to this point now and this point, what they are? They are my sigma max and sigma min. Because I have drawn this picture to some scale with respect to the stress values. So I can directly read these lengths on my picture and scale them back to the stress values, and that will directly give me this principal stress values. Then what? The maximum stress. If I draw a perpendicular here, it will reach the topmost point, and that is my maximum shear stress which can occur in this condition. Okay, and so that is the plane on which the maximum shear stress is occurring. Now the point is how to know on what plane they are occurring. So see this. If you measure this angle now, suppose this angle is say theta. Okay. Now that will, what in English this tells you is, if you rotate this axis by theta over 2, okay, theta over 2, if you rotate this axis in this direction, in this case it is counterclockwise, then you will reach the plane where the principal stresses are occurring. That means on the physical domain, so that is the Mohr circle domain, this is the physical domain. On the physical domain, what it tells you is, if I consider a elemental square like that, whose x dash axis is making an angle this theta over 2, the theta which I have measured here. So that theta over 2, if I go to a elemental square like that, I will get the maximum sigma. And then from here, if you go 180 degree on the Mohr circle, this is 180 degrees. So that corresponds to 90 degree on the physical condition, and that brings you to this plane which will contain the sigma min. Okay. So that's how you can answer the question, where are the principal planes. So you just have to measure these angles. Okay. And yep, that pretty much the information which you always require from a Mohr circle. And then suppose you have to look for the stresses on a given angle. Suppose somebody asks you that if I go to a plane which is say some angle alpha with the original x-axis, then how do you get the stresses there? So this is your original plane, right, from where you have to measure everything. So alpha means now you have to go for 2 alpha on the Mohr circle. So you read 2 alpha on this, and so this is the point which makes 2 alpha. Then you read sigma x for that, sigma x for 2 alpha, and tau xy for 2 alpha, and that will give you the state of the stress at that particular orientation. So that means once from this you have drawn this Mohr circle to some scale, you can now read all the information that you require. In fact, if you are these equations are difficult to remember, but in fact you can directly write these equations from these this picture. Okay. For example, suppose I come to this equation. Yeah. Okay, principal plane at what angle? 2 tau xy over sigma x minus sigma y. Let's see, can you read it from the picture? Sorry. So now you see here. So this is the point, and from and then if you see this length is tau xy, and how much is this length? Let me. So this length now is, how much is that? Now this minus this, so this is total sigma x minus sigma y, then this is half of that, So this length is, so now tan of that theta, tangent of that theta, which is nothing but 2 theta there, will be equal to what? Tau xy over this by 2, that means sigma x minus sigma y over 2, that means 2 xy here in the numerator. So that's what is the formula for getting the principal planes from the measured axis. And similarly, if you are thinking about the principal stresses, so this is sigma x plus sigma y plus this radius. Now how do you get this radius? See this. This is nothing but tau xy square. So this length r, right? R, how can you get from this? This length you have calculated to be this. So sigma x minus sigma y over 2. So its square plus tau xy squared under root. So that's the r, which is the value of the maximum shear stress. And you add that length with sigma x plus sigma y by 2, you get the maximum sigma. You subtract that from this average, you get the minimum sigma. So all the information is available on a single picture once you draw the Mohr circle. So that's how this picture is so beautiful and so informative once you have drawn it properly. So in fact, in next segments we will draw some specific Mohr circle under specific conditions to infer results from there. Okay, so see you in the next segment.